So for the self-controlled case series, there are some requirements that we have to meet in order to be able to use the design. So first of all, we need to have a well-defined observation period. So we need to know when do we start observing patients and when do we finish observing them, because I need to be sure that during that period I would be able to see if they had both the exposure and the outcome and when they had it. The exposure time needs to be well defined, because if I'm going to split their observation period up into exposed and unexposed, I need to know when to do that. The period of high risk needs to be known to some extent. So for the vaccine study, they knew in advance to break down the period into the first 2 days, 3 to 14 days, and then later periods. So we need to think in advance, what should those periods be? We would need to do that in any other kind of design as well. And the outcome itself also has to be easily dated, so we know exactly when it happened, because we're going to put it precisely on this observation period timeline. Yeah. There's no need for everybody's risk period to be the same length. So if we're looking at a drug treatment that could go on, like an antidepressant that could go on for some long period, it's fine for people to have different length exposure periods. Okay? So why don't we always use this method? Because if it means that we can forget about between person differences, then surely we should be using it more. Well, the trouble is, we'll come on to in a minute, there are some definite advantages. So because we're making these comparisons within patients, the between patient differences become irrelevant. And that includes the things that we can measure, like gender, gender, smoking status, that kind of thing. But it also includes things that we can't measure, like genetics or diet or exercise, which will often not change that much over an observation period. So it can remove a lot of confounding by indication. Things that do change over time, and typically that's things like age, or anything else that we can measure and that we thought about in advance, like your point, we can then adjust for those separately within our model. So we can adjust for other confounders that change over time, as long as they're measurable. But the limitations can be quite major. So I already mentioned that we have to be able to define our exposure period well, and our outcome has to be well dated. So this method won't work for treatments that people take as needed. So if somebody has migraines and they get a prescription for an anti-migraine pill, they're only going to take it when they think they're going to have a migraine. So on my observation period, I don't know when to put the high risk period. So I can't use it for those kinds of treatments. Similarly, an outcome where the exact start date is difficult to measure will also not be appropriate for the design, because again, I won't know where to put it on the timeline. So things like cancer, which we typically don't know when that starts, we won't use these designs for that. There are also some major assumptions which we started to talk about in Massao's session earlier today, which we have to make these assumptions to do the study, but we need to think about whether they're reasonable. So two which might not be valid are, first of all, that having the outcome of interest doesn't influence the chance of being exposed to the drug again in the future. And I'm going to illustrate that in a second with a diagram. But the problem is, if I have the outcome, so let's say I wanted to investigate whether or not statins are preventing heart attacks. If I have a heart attack today, hopefully you'll take me to the hospital, which is not very far away, which would be good. But then afterwards, my doctor might put me on a statin. Yeah? I think that would be sensible. So me having a heart attack would definitely change my likelihood of receiving the treatment in the future. Yeah? That means that the observation time after the event is going to be biased in favour of being treated. Yeah? It means that the baseline time beforehand will have an artificially high rate of the outcome. So I'm not going to be able to make a good comparison between my high risk and low risk period, because there's something very unfair about the post outcome observation time. Does that make sense? The second major assumption is that having the outcome of interest doesn't affect the end of the observation period. Okay. So here's how this looks on a timeline. So the first is, if the event increases the risk of mortality, so death itself would be a good example, or something like a stroke, where the risk of dying shortly after a stroke is quite high. It means that we then can't observe what would have happened if the patient hadn't died. And sometimes, not always, this can then lead to a biased result. And it can be very difficult, if not impossible, to predict whether the result is biased. So we ought to avoid the design if we think there's a high chance that it increases mortality. In the second one, here I've got an example where it's the other way around. Maybe having the outcome means that you're then not likely to receive the exposure in the future. So this could be something like, well, the GI bleed that Masao was talking about this morning with antidepressants. Once doctors knew that this was a problem, if somebody had already had a GI bleed, they then might avoid antidepressants in the future. It would mean we then had a long period of observation with no exposure and no outcome, because they already had the outcome earlier on. So we would have an artificially low rate of the outcome during baseline time, and this would be a problem for the design. So how do these assumptions and limitations apply in reality? So events that will influence subsequent exposure, this could include things like, if we wanted to look at suicide attempt and whether it's associated with antidepressants, and this has been a live research question for many years. This design wouldn't be very appropriate, because if I had a suicide attempt, then again my doctor might then put me on an antidepressant, so the outcome would lead to the exposure, and this would be a problem. A more subtle variation of this could be that an illness or an event may prevent somebody from receiving a vaccination in a short period of time. So it might be that if I've got some problem today, it may mean that for the next week or 2 weeks, I'm unlikely to receive a vaccination. We can handle short delays, but if it meant that I would then never receive the vaccination, this would be something that we couldn't handle in the design, so we would have to use another method. And we talked about some outcomes that will often lead to a short-term risk of death, like stroke. And again, if we think that this is likely to be a problem, we should just not use this method. There are some quite sophisticated statistical techniques that people are developing to try to circumvent or get around these problems. And there's a good reference here that talks about the method in general, if you're interested in finding out more. There's also there's a university in the UK called the Open University, and this is where both Paddy Farrington and Heather Whitaker did most of the development work for this method, and they have a lot of open source code lists and programs that you can use with statistical software to use this method to apply to your own data, and they're all downloadable from this website. Okay, so I'm going to move on to the case crossover design in a second. So are there any more questions about the self-controlled case series before we do?
Regarding to the second assumption, the observation period after the outcome. So we have such a air pollution, some environmental exposure. Some research use the pre and post bidirectional sampling. If the outcome is fatal, for example, myocardial infarction or death. So in this case, they mentioned the bias about the time tendency is smaller in bidirectional sampling rather than unidirectional sampling. So usually, is it necessary to fulfill the second assumption about observation period in self-control study?
In fact, we've in work that we've been doing along with Heather Whitaker, we've tended to find that outcomes that can increase the risk of death, but only in a small proportion. So I don't know what it's like in Japan, but in the UK, the short-term death rate from MI is less than 10%. So what we've tended to find is that that doesn't lead to a biased result. So although it partially breaks that assumption, it doesn't seem to lead to a major bias, and maybe it's the same with the air pollution.